Okay, in this new chapter, we're going to take a look at the mole. Okay, the mole is not this mole, this picture that you see here, and neither is it this mole that you see here. Okay, so we are looking at something different, something that you can't really see, but something that you can calculate. Okay, so this whole chapter is called the mole, and there are a few parts to it. The first part will be relative atomic mass, called AR, followed by relative molecular and formular mass, and then we'll take a look at percentage composition of compounds, and what is exactly the mole, and molar mass. Then how do we derive chemical formulas for different compounds and all the different substances. And of course, for gases, we seldom use mass, we use volume. And for solution, aqueous state, we use concentration. Okay, so let's take a look at the first part, relative atomic mass. Okay, so the learning objective for this particular lesson will be on relative atomic mass. Okay, that is for atom. And when it comes to molecules, we use relative molecular mass. An ionic compound, we use relative formula mass. And then we'll take a look at percentage of a particular element in a compound. So for example, I have NaCl. Okay, I'm interested in the percentage of sodium, for example, in a compound called NaCl. So I'm just looking at what is the mass of Na only in NaCl. So we learn in science that all matter has mass. Okay, so for example, your table salt, NaCl, it also has mass. Okay, so for example, this ionic compound, NaCl. Okay, what contributes to its mass? Okay, it's definitely the sodium, definitely the chloride here. Okay, so for sodium itself, okay, sodium, it has mass. So what contributes to the mass of sodium atom? What contributes to the mass of chlorine atom? Okay, so here we are looking at relative atomic mass. Okay, only one atom. And in an atom, okay, there is proton, there is neutron, and there is an electron. Okay, so I want you to recall the first topic called atomic structure. Okay, so an atom made up of 3 subatomic particles. Recall protons, neutrons, and electrons. And we also take a look at the symbols, the relative mass, and the relative charges for all of them. So for proton is P, neutron is N, electron is E. And without looking at the answer, test yourself. Check. Do you recall the relative mass of these 3 subatomic particles? Okay, so for proton and neutron, they're in the nucleus. They each have 1 unit. Electron is negligible, very light. Okay, they fly around in the electron shell. So they have a relative mass of 1 over 1840. So the charges I'm going to go through is plus 1, 0, and minus 1. If you want to be a subatomic particle, you be a proton so that you stay positive throughout. Alright, so question is, what is relative mass? Relative to what? Okay, so there's no unit. You don't need any unit for it. Okay, so for relative atomic mass, what are we comparing to? How are they calculated? Okay, so for chemistry, okay, we use a standard. Okay, so for example, if you take a look at this weighing balance, okay, the fruits, okay, they are 1 kg. How do I know it's 1 kg? Because compare relative to the standard weight. The standard weight is 1 kg, so relative to weight is 1 kg. Okay, so from here, this weighing balance, I know that the fruit is the same weight. Okay, so in atomic structure, recall, nuclear number is actually also called the relative atomic mass. Okay, and they are the number of protons and neutrons in the atom, because this proton and this neutron, okay, they have a relative atomic mass of 1 unit. So nuclear number is the total number of these two together. So in your periodic table, the bigger number, okay, the bigger number will always be the relative atomic mass of the atom. Okay, so this 7 is the relative atomic mass for lithium, and this 4 is the relative atomic mass for helium. So let's take a look. Definition of relative atomic mass. So now we are looking at what is exactly relative atomic mass. Okay, so we use the symbol called AR, and this R is a subscript. Okay, and it's the average mass, okay, of one atom, Okay, it's the average mass of one atom compared to 1/12 of the mass of one carbon-12 atom. Okay, so fill in the blanks in your notes. Why do we use average? Because we are taking into account of all isotopes. Okay, average of all isotopes. Okay, and because we are comparing atom by atom, so we talk about one atom. And we are comparing to carbon. So why do we use carbon? Because they are very abundant. Okay, they are everywhere. Okay, so it's easier to use carbon as a standard. But carbon, okay, it has different um, isotopes. I can have carbon 12, I can have carbon 14. So there are two kinds, okay, of isotopes. In fact, there are other, just that these two are more significant. Okay, so there are two kinds. So which one do we use to compare as a standard? We use the 12. Okay, we use carbon 12 as the standard. And for carbon 12, it has a total of 12 units. Okay, so that is why we use this term called 112 to signify that we are actually comparing one unit out of these 12 units. Okay, if you really don't understand what's this whole idea about, it's okay. You just memorize the definition. Okay, so the AR can be obtained from the nucleon number. Okay, take note of the spelling. And it has is a ratio. It has no units. Okay, so once you see the term relative, it means that we are comparing it to something else. It has no units. Okay, so let's take a look. Okay, whenever we are talking about relative atomic mass, we are always talking about it in terms of like a weighing balance. Okay, comparing to a standard. And this particular standard they are referring to is your carbon 12. Okay, so carbon 12 is the standard. Okay, so carbon, like I mentioned, is the most common form. That's why we use it. So it has a total of 12 units. And now we are just taking one unit to compare. Okay, so take some time, complete this page in your notes, okay, with the help of your periodic table. So what is the relative atomic mass of these elements? Okay, when we talk about relative atomic mass, take note, we are always looking at one atom. Okay, so for example, oxygen, we are looking at O. We are not looking at O2. Okay, so please don't write 32 inside your notes. Okay, we are looking at one atom only. So it's not oxygen gas, but just oxygen atom. Okay, so complete the rest and check your answers. Okay, moving on. Here we see an odd number, which is chlorine. Okay, so chlorine is 35.5. And the question is, why is chlorine 35.5? Okay, so why is it that the AR is not a whole number? Okay, recall what was the definition of relative atomic mass that we mentioned earlier. I'm going to show you a short video, okay, to help you to recall.
This number which appears on the periodic table. The number seen on the periodic table is the relative atomic mass, or the AR. The relative atomic mass of an element is defined as the average mass of the naturally occurring isotopes of the element relative to the mass of an atom of carbon-12. On the periodic table, it is the same number as the mass number. In basic terms, it is the average mass of the isotopic forms of the element. When we think about this, we must remember that isotopic forms of elements have different values for their naturally occurring abundance on Earth. For example, let's look at the isotopic forms of chlorine. Some chlorine atoms have a mass of 35, and some have a mass of 37. In most cases, to take a simple average, you would just add the values together and then divide by the number of values. In this case, it would be 35 plus 37 divided by 2, and you would get an average of 36. But this is not how you calculate the relative atomic mass. We need to remember that we are talking about number of atoms. There are a certain number of chlorine atoms with a mass of 35 and a certain number of chlorine atoms with a mass of 37. However, within a sample, the levels of each isotope are not equal. So we take this into account when we are calculating the relative atomic mass, so that we are calculating a weighted average. Naturally occurring chlorine is made up of 75% chlorine 35 and 25% chlorine 37. This can be shown to you on a graph to show abundance data. where the relative isotopic mass is shown along the x-axis and the relative abundance is shown on the y-axis. So say we had a simple sample of 100 atoms of chlorine. We would have 75 atoms of chlorine 35 and 25 atoms of chlorine 37. We first find out the total mass of the sample. We do this by multiplying the mass of each atom by the number of atoms present for each isotope, and then we add them together. For chlorine 35, there are 75 atoms, and for chlorine 37, there are 25 atoms. So the mass of 100 atoms would be 75 times 35 plus 25 times 37, 3,550. The mass of one atom will be the mass of the total number of atoms divided by the number of atoms. So the mass of one atom of chlorine would be 3,550 divided by 100, 35.5. The relative atomic mass has a value closer to 35 because there are more atoms of chlorine 35 than chlorine 37. It is a weighted average. So the relative atomic mass of an element is defined as the average mass of the naturally occurring isotopes of the element relative to the mass of an atom of carbon-12. On the periodic table, it is the same number as the mass number. The number is a weighted average, and when calculating its value, the proportion of an isotope in a sample must be taken into account.
Okay, from here you can recall that chlorine is 35.5 because Ar is an average mass of all atoms. So we are taking into account the isotopes. Okay, so take some time, 2 minutes, complete this. What is the Ar of rubidium? Okay, we have done this question before. So do you get 85.6 round up to 1 decimal place? Okay, so in this case, we are taking into account the average of rubidium. So we don't just add them together and divide by 2. We take into account the percentage abundance of rubidium 85 and rubidium 87. So we have completed Ar. Okay, now let's take a look at the next part, which is relative molecular mass. Okay, so we have finished relative atomic mass. Okay, we are talking about mass of one atom. What happens if we have molecule? Okay, so we're going to take a look at relative molecular mass and relative formula mass. Okay, so question is this. What will be the relative molecular mass of a molecule or a compound? Okay, now that it has more than one atom. So, relative molecular mass, the definition is similar to relative atomic mass. The symbol instead of Ar is now Mr. Okay, and it is also the average mass of one molecule. Same thing, we always compare to the same standard. So in this case, we are also comparing to carbon-12 and we are comparing it to 1/12 of the mass of one carbon-12 atom. That means this carbon-12 atom has 12 units. You are using 1 unit out of the 12, okay, to compare. So Mr is actually just a combination of all the Ar together. Okay, likewise, it is a ratio. It has no unit. So very simple. Okay, for example, now we are talking about molecules. So let's take a look at oxygen. Okay, so oxygen formula is O2. Okay, the relative atomic mass of oxygen is 16. So one of them is 16. Now I need to multiply by 2. Okay, multiply by 2. 2 times 16 is 32. So this whole topic, you will need your calculator. You must have your periodic table with you. Okay, and of course, you need to remember the formula of the molecules and compounds. Okay, so whatever that we have learned so far, do not forget. So 1 minute, take some time to complete this whole table and check your answers after this. Okay, so do you manage to get your answers for all the blanks? Okay, so moving on. Okay, what about relative formula mass? So why is it that there are two names? Okay, formula refers to average mass of one ionic compound. Okay, and likewise, we always compare to the mass of one carbon-12 atom. Okay, so definition for molecular mass and formula mass are the same except for this portion here. Okay, so now we are looking at ionic compound instead of molecules. So how to calculate is the same thing, just the sum of all the AR of the atoms. Okay, it is a ratio, it has no unit. Okay, so 5 minutes, take some time to complete this page. Okay, so to guide you along, we will do the first example together first. Okay, so for example, sodium chloride. Okay, you need to ask yourself, what is the relative atomic mass for sodium? Okay, so sodium will be 23. Okay, and then chlorine is 35.5. So together, relative formula mass is 58.5. Okay, so try to do the rest. Now, at this part, some of you might be thinking, what is this dot here? Actually, this dot, if you recall, it comes in the topic of salts. Okay, so what does this mean? This means that I have copper 2 sulfate, right? Copper 2 sulfate. And this copper 2 sulfate, it has 5 molecules of water bonded to it. Okay, it has 5 molecules of water bonded to this ionic compound. So if I want to calculate the relative formula mass, okay, I need to take into account the water molecules. Okay, so what this means is that I will calculate 64, okay, for copper, 32 for sulfur, 64 is the 4 oxygen atoms, and then because the water molecules have weight, okay, they have mass, so I must include them inside. Okay, so why does this occur? If you recall your crystallization, this copper 2 sulfate crystal, right, they are blue color because the water molecules are trapped inside. Okay, so the water molecules are trapped inside, it contributes to the weight, right? So we need to add them together. Okay, so try to see whether you can calculate for iron 2 sulfate. What is your answer? So do you have this answer? So this is that. Relative atomic mass, relative molecular and formula mass. Now we're going to move on to the third part, which is percentage composition of compounds. Okay, the third objective of this lesson. Okay, so what is percentage composition? Now, percentage composition is very similar to what you learn in math. Okay, so let's take a look. I have a block of red Lego brick and blue Lego brick. So if I were to ask you, this combination, what is the percentage composition? Do you agree with me that this model here is made up of 50% red and 50% blue? Agree, right? Okay, so moving on, I have this model here. Okay, and I'm going to ask you, what is the percentage composition of red Lego block? And your answer is 75%. And I would ask you, how do you get 75%? Then you will explain to me and say, oh, because there are 4 blocks, right? And 3 out of 4 blocks are red color. So 3 out of 4 times 100%, because I'm looking for percentage, is 75%. And then if I would ask you, so what is the percentage composition of blue Lego bricks? And then you answer, okay, percentage of blue Lego bricks will be 100% minus 75%, or 1 out of 4 times 100%. Okay, so this is for your blue Lego brick. Now I'm going to change my question. I'm telling you this, that this total mass of the model is 200 grams. And one red Lego is 50 grams. One blue Lego is 150 grams. Now I'm going to ask, what is the percentage composition by mass? So out of this 200 grams, what's the percentage of it is contributed by the red Lego brick? Pause the video, write down the working, find out the answer. So in this case, is your answer 25%? And how do you get 25%? Because you are using the mass of red Lego brick over the total mass multiplied by 100%. Okay? Now what about blue Lego? So what is your answer for blue Lego? So in this case, blue Lego is 150 over 200. So out of this 200 gram, 150 gram is contributed by the blue Lego. And therefore, the percentage by mass is 75%. Okay? So far so good. Okay, if it's good, you put a thumbs up and I will see it. Okay, very good. I see thumbs up. So let's move on. Okay, now I have this model, 300 grams. Okay, likewise, no change. One of them, for the red one, is 50 gram, and for the blue one is 150. So if I ask you percentage composition of the red Lego brick, what will your answer be? How do you calculate your answer? Okay, so you will use 50 grams times 3. Okay, so 3 Lego brick, total mass of the red one is 150 divided by 300 grams. And I can say that 50% of this whole 300 gram is the red Lego brick. Okay, then blue Lego brick, 150 gram divided by the total mass times 100% and you will get 50%. So 50% of this model, the mass is contributed by the blue one, and then 50% is contributed by the red Lego brick. So percentage composition of compound is the percentage by mass of an element in a compound. We are interested in what is the mass contributed by an element, let's say in a compound. So this is the formula used. Okay, it is the same as what you have done for the Lego bricks. Okay, it's just the mass of the element over the total mass of the sample times 100%. Okay, so let's try some examples. So let's say you are given this compound called NaCl. Okay, so it is like the model given to you. Okay, so the question asks, okay, calculate the MR of the compound, or rather, calculate the total mass of NaCl first. Okay, so the total mass, you will use the relative formula mass, which is 23 plus 35.5. So the total mass of NaCl is 58.5. Okay, total mass. So I'm interested to find the mass of the elements. Okay, so how much of this 58.5 is contributed by sodium? How much is contributed by chlorine? Okay, so we'll take a look. So for example, okay, I'm interested in sodium. So for sodium, I know that it's 23. Okay, so 23 divided by 58.5 multiplied by 100%. Okay, so out of this 58.5, 39.3% is contributed by sodium. So if you want to work backwards, you can also do the same. So if the question says that, okay, 39.3%, okay, of sodium chloride is made up of sodium. Okay, total mass is 58.5. Calculate the mass of sodium. Then you calculate it and realize that, oh, you will get 23. So you can work backwards to check your answers. Okay, so whatever we learn using the Lego bricks, okay, you can apply here. So if I will change my question and say, okay, what about percentage of composition for chlorine? Okay, so instead of 23, I use 35.5. Okay, so if you take a look, okay, I will use 35.5 divided by 58 times 100%, okay, to realize that, okay, 60.7% is contributed by chlorine. Okay, so pause the video, complete the question, okay, in your notes and see whether you understood this concept. Okay, so for copper 2 sulfate, okay, first of all, you need to find out the MR. Okay, so the MR of this, okay, the MR of this compound is 160. So you calculate. So the total mass, okay, the total mass is 160. Okay, 160. So out of this 160, okay, I have 64, okay, contributed by copper. So total mass is 160. 64 is contributed by copper. So 40%. 40% is the percentage composition of copper. So if you are given a compound of 32 gram, okay, if you are given a compound of 32 gram, okay, 40% 40% of this 32 gram is your copper. Okay, so what does this mean is that, so out of this 32 gram, okay, 40% is contributed by copper. Okay, so let's look at this working again. So total MR of the compound is 160. So copper 2 sulfate is 160. This 160, 64 units of it is contributed by copper. So is to say that 40%, okay, is contributed by copper. Okay, so if you're given 32 gram, okay, and the question asks, okay, if the question say, what is the mass of copper? in CuSO4. Okay, so if the question asks for this, what's the mass of copper in copper 2 sulfate? You know that 40%, okay, is made of copper. Okay, so from the percentage of composition, okay, I can conclude that actually this 32 gram, right? 12.8 gram is contributed by copper. Okay, so this is how you do it. Okay, but of course in this question, we are only interested to look at the percentage by mass. So we are looking at the percentage. Okay, okay, so for the next question in your notes, page 5, then let's try this question. Okay, so the question will tell you what is the compound. And if the question never give you the formula, the first step is of course to find out the formula. Okay, otherwise in this case, the first step is always to calculate the MR. Okay, you need to calculate the MR to find what is the total mass. Okay, so in this case, I have copper 2 sulfate and I need to take into account of the water. Okay, so there are water molecules being bonded together. So I calculate my MR. Okay, 64 plus 32 plus 4 times 16. That is for your copper 2 sulfate. And then the 5 times 18 is for the 5 water molecules. So the total MR is 250. Then the question asks, what is the percentage of composition for water? Okay, so I'm interested in H2O. Okay, so how many H2O molecules are there? Okay, there are a total of 5 of them. Okay, so if I take a look at this formula, this is the part that I need to take note. Okay, so if I do the formula, I will have my 5 water molecules, which is 5 times 18. Okay, I'll get 90. So out of this 250 units, okay, 90 units is made out of water. Okay, so 90 divided by 250 times 100% to calculate the percentage composition. So in this case, okay, the answer will be 36.0%, okay, to 3SM. Okay, okay. So in this case, okay, we have already learned the definition of AR. Without looking at your notes, okay, try to recall what is the definition. Okay, so this is the definition of AR. Okay, moving on. Okay, we look at how to calculate for molecules and ionic compound. So for this one, it's only for atom. Okay, so take note, this one is only for atom. Okay, so the next one, MR, is for molecules or ionic compound. Okay, try to recall this definition without looking at your notes. Okay, so O level, when they say define AR, define MR, okay, these are your learning objectives. You're required to know the definition. Okay, of course, when you're learning something, always seek to understand and not memorize blindly. Okay, then the last part of the lesson, we learn about percentage mass. Okay, we are always interested in what's the composition of this element in a compound. Okay, actually, we are always interested in composition. Okay, when we buy items, we always look at the ingredient list. Okay, if you look at your sweets that you buy, right, usually the first ingredient is of the higher percentage. Okay, so we are always interested in the percentage composition. All right, so this is the end of the first part of mole.